Good morning, everybody. So yesterday we talked about plasma instability, and today we try to show you a more dynamic phenomena of plasma instability, and then we show you to develop some kind of a linear stability theory. So every time you see a new phenomena, such like this, where is laser point? Does not show up anymore. Maybe change. So, for example, you can see that if you take a single shot about that the plasma discharge and between that the electrode, you can see a little spike. And each of this spike is a clear indication that there are charge accumulate on the electrode. And that charge will create a streamer flying to the other electrode. So this is that I think that is a clear indication and how that the dielectric barrier discharges behave. So if you take a single shot and compare that mixture about methane, oxygen, and argon, and compare to the oxygen and argon only, you can see that this is an unsteady time-dependent measurement. You can a lot of streamers is happening, and for that the mixture with fuel. So again, it's clearly indicating that when you have a fuel in the mixture and the plasma combustion chemistry interaction, that create a stronger that the plasma discharge and create that the streamers on the surface. Now, so this is the figure I showed you. So even you say I'm going to change for a pentane, and pentane has a lower temperature chemistry. And in that case, you see that without plasma, and everything becomes uniform. But with plasma, the instability getting even stronger. So it's a clear indication, again, saying that not only that plasma combustion coupling can enhance plasma instability, but also saying that if the fuel has a low temperature chemistry, and this instability is getting stronger. So that worth attention about how that the reactivity of a mixture that is going to change plasma dynamics. So you want to understand this, and I have another student, and Hontao, and he's good at mathematics. I said every time when you see a new phenomena, you try to develop a theory and give a new name. So that's what I was advised. And when I came to Princeton, Professor Harvey Land said, when you have a new phenomena, or when you have a new method or a new theory, just give it a name so that people will remember you and distinguish you from others. So we try to do something called plasma thermochemical instability. So you can write down that the governing equations like electron number density, ionization, and attachment, and then convection, detachment, electron recombination, ion recombination, and diffusion. And you can write down all the neutral molecules and ions and neutral molecules, and then energy conservation. We have Joule heating, which is a convection, combustion heat release, vibration, translational relaxation, and then diffusion. So this is our linear equations. And anybody take a good ordinary differential equation and do a linear stability analysis, you will be find that this is easy to find an instability solution. And to do that, you can find that how the electrical field, E over N, change as a function of temperature, as a function of electric field. You can perturb the temperature as some kind of a wave function, and perturb that the electric field as the same wave number. And you try to plug in all these parameters back to the governing equation and try to find that the eigenvalue of that a complex variables, either it's the temperature or electron number density, and they become 0. When they become 0, and you can find that the critical conditions of plasma instability. So here is basically showing you how that the heat release from combustion. So here that the real value is above 0 means unstable, below 0 means stable. So if you have a combustion heat release, you can see that the stability move to the small current. That means that it promotes instability. If the combustion process is endothermic, that will stabilize the plasma and making the plasma stable at a high current. If you look at the vibration translational relaxation timescales, for example, this is at the 10 to the minus 4. If the vibration translational or vibration rotation energy transfer is fast, that means that the non-equilibrium becomes equilibrium faster and instability will develop. So so therefore, you can see that this kind of linear stability analysis gives you a very clear indication what are the major factors that are going to affect instability. So then you can start to show that how the electric field and depending on the current. And so if you make a derivative of the electric field as a function of current or conductivity, you see dE dI. And you can say that the dE dI equals 0. At this point, it is separating that the stable regime and unstable regime. So dE dI is current. The current can be written in a way of dE into that the conductivity, because that is I is a conductivity as is a function of conductivity. And to do that, and then you will find a instability equation. That is that the conductivity of the plasma, that means that as a function of electric field. So you have this term, this one that is basically is ionization rate. That means how that the Townsend breakdown is happening. And this term, basically nu ij, is the reaction coefficient of the plasma chemistry. So this basically said how plasma chemistry will be affected by the electric field and E over N, and the mixture. So here is a term. You basically show that this is a convection, is a cooling effect, or heating effect. This is the vibration relaxation. This is the vibration translational relaxation. This is the enthalpy change due to combustion and kinetics, and normalized by Joule heating. And this is that and the whole thing minus 2 equal to 0 means that the neutral ability. So this basically saying that you have combustion heat release and then a vibration relaxation and plasma chemistry coupling with combustion in this term, they're all going to affect that the onset of instability. So, so that's too much. So you can say, so once you know that, you can write down, for example, a non-equilibrium plasma is the number density, this is the energy equations, and you try to understand what reaction is the trigger instability. So in combustion, basically, everybody knows that the computer singular perturbation method or sensitivity analysis or flux analysis has been used. Well, we can extend this thing, for example, using a CSP, the computational singular perturbation method. You can write down the governing equation in ordinary differential equation like dy dt equal to gy. Here, the y is a variable of electron temperature, electron number density, combustion species, and then temperature. And then g is the reaction rate. It's the same as combustion. You can do the same thing what you learn in combustion. You make a derivative of the source term as a function of Jacobian as a function about the variables. So this is a Jacobian. This Jacobian dictates what is the time scale that each reaction mode is going to proceed. So this is that the source term make a derivative to that the variables. This is that Jacobian. You decompose the Jacobian into a diagonal matrix like this, and then left eigenmatrix and the right eigenmatrix. So this diagonal eigenvalue determines that the time scales of each reaction mode. And you can decompose, for example, that this equation, decompose equation, you multiply the left by B and the right by the B minus B. So you can divide this coupling governing equations into a decoupled ordinary differential equations. So this lambda, again, is diagonal, and all this F is a mode, and that mode is decoupled from each other, so that you can find each mode, which mode become important to drive that instability. So if that the eigenvalue is positive, and then you can say the system becomes unstable. Is negative, the system is stable. So you do this kind of CSP analysis. We call it thermochemical mode analysis. And then you can really find that what is that reaction and is important. For example, this is the electron number density, ion number density, vibrational mode, and temperature. So you find that one of the mode, F mode, is important, is eigenvalue is positive. Then you can project this eigenmode back to these different vectors and see which vectors project more to this unstable mode. So to do that, you can see that which reaction mode becomes important. So for example, let's say we have a nitrogen-oxygen mixture. We have adding some kind of hydrogen into it, or that we can adding hydrogen into it, but my temperature right now is high. So try to see that how fuel is going to change the instability mode and how temperature is going to be stabilize the instability. Here from this comment, you can see that this is the thermal instability, this is the thermochemical instability because you have fuel, and here that when you raise temperature, and then the plasma becomes uniform. So yesterday somebody asked me, so if I want a plasma to be uniform, to not unstable, what should I do? Okay, I said, okay, you can reduce the pulse time and reduce the gap distance of the discharge. Here is another parameter you can do. It is that they raise the temperature and the plasma becomes uniform. And also you can change the composition and control the thermochemical instability. You can make the plasma uniform. So I think that this show you that how that the theoretical analysis. Here you can see this is the nitrogen-oxygen mixture with no fuel. This is the real eigenvalue, which is positive. You can see how much eigenvalue is here is positive. But when you're adding hydrogen into it, you can see that the real value, you have many, many more positive real values is happening, which behave differently. So if you increase the temperature to 825, you can see that the positive unstable eigenvalue start to decrease. So that is you can also point out what react species. For example, you can generate a species index. Which species is critical to instability? You find that, okay, the hydrogen vibrational state, oxygen vibrational state, and then you have H and OH radicals, and then particularly N2AB and O2 singlet. So these are the 3 reactions we talked about yesterday, and they show that this is an important mode about that to make that plasma unstable. So I think that the knowledge in combustion we learned in terms of eigenvalue analysis or sensitivity analysis, it can be applied to here to identify that reactions. I think that is very good for the plasma community, and they help them to understand, provide a tool, and they can understand this instability sources. I try to show you that how that, then I asked that Hantao to do a one-dimensional modeling. So you have electrode is positive, and then you have a cathode is negative, and you have electrical field, let's say assume is uniform coming here, and then you have convection going there. So you are studying that plasma discharge in a mixture with fuel, and then you have a convective heat losses. And this geometry makes you very simple one-dimensional so that you can avoid the two-dimensional simulation. So you can consider that they reduce the electric field about 80,000. That you want to see that the important that the plasma chemistry, and you try to see that this reaction, electron attachment, and how to see their effect, and the vibration translational reactions try to affect the instability. So you can write down the governing equation. This is very easy, just like combustion. The only thing different is here is that the drift motion. This is that you can see mobility, electron number density, and the electric field, they will move. Diffusion, and then everything is the same. And vibrational mode is here. You try to look at a vibrational coupling. So that satisfies that the charge conservation equations. This derived from Boltzmann equation, everybody know. So there are two possible solutions in this. One is that you start to see a non-uniform contraction. Something is very high in the center, and the surrounding is very, very low field. Another one is that you have very uniform homogeneous electric field, showing that the plasma is stable. So stable, contracted. So, and then you can plug in all this combustion chemistry everybody know, and this hydrogen chemistry, and you can plug that a simplified electron ion chemistry in plasma, including electron impact dissociation, ion recombination, and this is that and also that the vibrational excitation. So this gives you some kind of a critical thinking about what is that the important reactions is going to affect your instability. So again, we compare this mixtures. Case 1 is just inert, and case 2 just fuel with nitrogen. And case 3, you have fuel but is lower temperature, and case 4 that you have fuel but temperature is high, and see how that changes that instability again. So the first thing I try to show you conclusion is that if you're looking at the electron attachment effect, for example, here you can see electron attachment to oxygen, and this reaction rate is 1.6 to 10 to the 31st. If you're looking at electron attachment to oxygen with water as a collider, and that reaction rate is a 2 orders magnitude is faster. So what does it mean? It means that you can see that if you have only have oxygen, and you will have that instability happening around that maybe 30, 20, 25, maybe somewhere here, 32, 30, 31, 32. That the plasma become unstable. Electric field is very high and suddenly drop, and then, but if you have water, you can see that the instability is extending. So it says that the electron attachment due to the collision with the water, they are going to enhance the plasma instability. So this is something we learn from it. So you can see that the critical value is increased from 30 milliampere and to 36 by considering that the electron attachment with collision of water. So this is conclusion 1, electron attachment and affecting plasma instability. And conclusion 2, that is the fuel, is that hydrogen replace that oxygen by hydrogen, and see how that the reactant is going to change. You can see that we have oxygen because that and we have a hydrogen, and the hydrogen chemistry and make it that the instability dramatically extended. So so you can see that instability extended from 30 to 20 because that in the oxygen, the electron impact association of a oxygen atom is dramatically reduce the attachment of electrons to oxygen. So if the electron does not attachment to a molecule, and then you have a shortened instability that makes the plasma stronger. So it's conclusion 2, that the reactant also matters. And so looking at the comparison with if you have hydrogen mixture, hydrogen, oxygen, and nitrogen. So here you can see that the onset of instability without combustion is about a 20, maybe 29 or 20 here. If we consider that with combustion, that means that the instability is dramatically reduced. So therefore, that the fuel oxidation that give heat release that dramatically that enhance that the plasma instability making that the plasma chemistry strong, and then make the system unstable. So this is what consistent what we say in terms of that experimental observation. So, and then we try to say, okay, so because we add pentane into it, because pentane has a low temperature chemistry, so what if we do experiment, and this is a collaboration between Hongtao and Yiguang at Movich at Ohio State. So you can see that the plasma, nanosecond plasma discharge, comparison with air, with dimethyl ether with air, at the equivalence ratio of 1.4. With air, you can see that with the pulses to 400, that the plasma is pretty much uniform. But with a dimethyl ether, and you can see that their plasma instability development, the instability will drive that and then it becomes a uniform. So here is interesting, uniform, instability, and uniform, and ignition happening. So what that says, this says two things, that low temperature chemistry accelerate plasma instability. Second, when that the plasma instability happening, and then the reactant mixture getting hotter, and in the plasma, and the plasma become uniform. At high temperature, plasma become more uniform. It is because that the diffusivity of the molecules that they stabilize the system. Diffusion is second order diffusion is always stabilize the system. You can see that it comes from instability. So therefore, that there is this picture gives you a way how do we predict and control plasma instability by control the chemistry, by control that the temperature. So what I conclude is that from this kind of experiment and study, I demonstrate to the plasma people, look, that the combustion or that the reaction of the mixture of reactant become very important. They not only just dependent on the plasma, but also they control that plasma dynamics. So this is that something I'll try to show you what is that thermochemical plasma instability. Is there any question? All right. So I think that we probably, right now we try to do, in the experiment, I have a graduate student using water and using ferroelectric materials, try to control plasma instability. Here is that when we developed this theory, and under the NSF funding, and I convinced my colleagues at the chemical engineering, I said that, okay, if we understand that the plasma instability, now we can have an idea how to control the instability. So if we can, for example, put a spray into the mixture and generate that the aerosol discharge. The aerosol has a coupling, not only that they generate radicals and from that the surface, but also that the electrons will attach to the surface. So therefore, by putting aerosol into a system, doing a CO2 and methane dry reforming with water, maybe adding some aerosol, then you probably can control the plasma instability at atmospheric pressure. So we write a research proposal in 2020 for National Science Foundation Energy Frontier Research Initiative with 6 people of us. And then next year, and we will award it, and we start to understand how that the water is going to be affecting the plasma instability. In gas phase, that's surprising that if you have a methane oxygen, if you're adding water, the plasma dissociated water into H and OH radicals, they promote the oxidation of methane, they drive that the instability dramatically increase. But if you have aerosol, how does that affect the instability? And that's a very interesting thing to see, how that electron attachment, for example, to the surface, they're going to affect it. How that the plasma interaction with that the aerosol is going to change the instability. So I thought that all these things that the combustion people look at a lot of spray and how to see spray vaporizing, how to the heat, but in the plasma that the spray is going to dramatically change the plasma properties as well. So I see there are a lot of opportunities to study that how this aerosol is going to interact with plasma. So that opened a new research area in terms of how do you make a material synthesis, how the dust plasma we are going to affect it, how that if you want to make a carbon from using plasma discharge of biomass, then how does that particles is going to affect the plasma instability and change the plasma properties. So I think that this open a lot of interesting questions and to address. So I want to say that the conclusion is that we developed observed and developed that the thermochemical instability really out of my curiosity when I read that news from rocket launching from Russia in 2019. And we using that the CEFRC method to show that there are the sharp electric field distribution and then streamer occurring between the electrode. And we developed a model for plasma chemical instability analysis and identify which species, which pathway will be important to trigger instability. And also we find that we can using low temperature chemistry, we using aerosol, a chemical field reforming that can control plasma instability. And I hope that through this section of presentation, you learn something similar to combustion, but impact another area. All right, any questions so far? Okay, so next thing I try to talk is that I'm make sure that I can finish it. So I try to talk that put the last chapter earlier than the modeling part. So the next part, I will probably spend about an hour and a half and talk about what is the status in terms of electrified manufacturing and of using a plasma or using Joule heating about electricity. So what I'm going to talk first is that is give you an idea what is electrified manufacturing, why it is a need today, and then we go to fundamental catalysis of plasma catalysis. And so some of you doing maybe ion combustion, that is not catalytic, but it's still heterogeneous oxidation process. Then we talk about the manufacturing CO2 conversion into CO2 reduction and into chemicals and ammonia synthesis. Then we talk about that plasma-assisted chemical looping and ammonia synthesis, and then materials manufacturing and upcycling about plasma and materials, and then a future research. So let's first looking at this picture. And this is the Department of Energy that published about CO2 emissions in 2020. So basically they say that is this where the CO2 coming from? So CO2 coming from commercial, residential, transportation. So these sectors, I think that it will soon be addressed by the electrified transportation using battery and e-fuels or biomass. Residential, you can use electrical heating in Europe. You got a lot of homes right now in France, particularly, and Germany, that you're basically using electricity instead of using burners. In Japan, that is also happening, and I was in Japan last fall. My apartment, basically, that they're using electricity and no natural gas anymore. So, and then the biggest part is that 30% of industry that produce cement and food, iron, steel, chemicals, refining, that remain to be addressed. And that process probably takes much longer than what we do for transportation sectors. So what is the opportunity? So if somebody wants to say, do this, I think that this one will be much more urgent to address and in terms of a decarbonization process. So this is that the proposal I was writing and a few years ago, try to understand that for using a non-equilibrium plasma, try to do ammonia synthesis, a plastic recycling, and CO2 reduction, and steel manufacturing, and involving multiple universities. Try to do develop that non-equilibrium interfacial catalysis, innovation of science, understanding photon excitation, surface charge, hot electrons and phonons, polarization of electric field, and try to understand that the plant system by interacting with industry. And then we try to do industry collaboration, MIT, Princeton, Stanford, UIUC, and the education part, and they try to address this thing. So this is something that we want to develop a team and to understand how non-equilibrium plasma can be used to do electrified manufacturing process. For example, if you have renewable electricity and if you have CO2, and you can produce hydrogen and oxygen from water, and then that hydrogen can be used with CO2 and or nitrogen to making ammonia. You can make methane if you want to, particularly Europe. If you don't have methane, you're using hydrogen and CO2 to make methane. And you can make methanol, particularly for China right now is interested to making hydrogen and CO2 to make methanol, particularly for the ships in river. And you can make a alcohol, C2 alcohols. You can also using the electricity, using oxygen and nitrogen in the air to make a nitric oxide, and eventually you make a nitric acid and fertilizers from here. So I think that this opened an enormous opportunity to making chemicals and using electrified process. But the key challenge, again, yes, we chatted yesterday that how do you make cheap electricity and how do you make the cheap hydrogen? So that is the big challenges. So, but using electricity instead of combustion, it gives you a disadvantage and also give you advantage. So let's talk about a little about thermodynamics. And in thermodynamics, everybody knows that if you have a reaction, and then there is a equilibrium, a constant, Kp, that is governed by that the product versus reactant depend on different pressure. So in other words, in chemical equilibrium, that you give me a temperature, you give me a pressure, I give you a product. So therefore, that your efficiency can be constrained by chemical equilibrium, and your selectivity will be constrained by chemical equilibrium. And is there anything we can do better? Well, so that was the last year when the Department of Energy called for proposal called Energy Earthshot Research Center. And I talked to people in Oak Ridge National Lab. Okay, I say, show them this diagram. So this is that horizontal axis, and equilibrium chemical synthesis is here. You give me a temperature, I give you a product. But if you can change that the temperature as a function of time, which is close to the reaction time scale. If you can excite the molecules and go to vibration, electronic excited, you can drive that the chemical synthesis from equilibrium to non-equilibrium, then open a new entire world to understand how non-equilibrium reaction systems is going to be impact of your chemical synthesis in industry. So, and we submitted a proposal, and we were awarded by DOE and for 4 years to understand how this non-equilibrium manipulation of a system affected the reaction in gas phase, affected the reaction in interface. Again, I want to say that, and there's a lot of opportunity for us. And if we have an idea and tell people a simple story, what you want to do, and do it differently. So I'll try to show you some example. And this is a person, and I'm Bin Hu, and from University of Maryland. And right now he's moving to Yale. I talked to him. He invented something like a carbon fiber heater. The carbon fiber heater is about less than 1 millimeter thin. And if you put electricity on it, they just heat it very quickly with probably 50 to 100 milliseconds. And then the radiation cool it down and to room temperature. So I thought this is a good example and to do a non-equilibrium synthesis. So here that the first example we did is that they're using this guy and they try to paralyze methane and making ammonia and see whether we can do better. So in combustion, for example, if you heat it very high temperature for methane, in the end you get hydrogen and carbon. But if I really want ethylene, not hydrogen, then you're stuck because the high temperature just drive everything, entropy, drive everything to carbon, right? So, but by driving this, because I can pump that the temperature to 2,000 Kelvin at 20 milliseconds, for example, and then I break down that the CH bond, or break down something. So then I quickly reduce it. If the process is exothermic, like ammonia synthesis, and if you drop the temperature, the equilibrium is going to shift toward the product. That makes the product yield is higher. So to do that, and then this energy and high temperature, lower temperature, the average temperature is somewhere here. You will see that the efficiency and of this non-equilibrium synthesis will be much higher than that using average temperature, just heat the process. And in fact, if you're using average temperature 815 Kelvin, the methane is not going to be pyrolysis at that temperature. You need a much higher temperature to do that. So this basically gives you an idea that you have a product. The product is driven by entropy. The process is going to increase the entropy, and it's a function of time. So there are, as a function of time, and you have different product product A, product B. So the question that product A is the intermediate product, which ethylene, for example, I want. I don't want to go to that the hydrogen and carbon, so I want stop once that ethylene is produced. So I can higher temperature and stop here, and then so I can produce selectively about product A. Is that clear? All right. So to do that, you can do this kind of pulse heating and quenching, so that it can produce the chemicals that you want. So this is one of the examples I show you that is plastic, polyethylene, polypropylene. And can we, if you're using plastics, if you're using combustion to heat it or pyrolysis it, and that the plastic, that CC bond, a CH bond is going to break, in the end it becomes like a coke and hydrogen and some kind of methane, right? So I don't want methane. I want, this is a polyethylene. I want to break down that polyethylene just to ethylene, so that ethylene can be reused to build a polyethylene again. But the same thing for polypropylene. If I can break down that the polypropylene into propylene, and the propylene will be a chemical, will be reused. So this is an example that we can show you if you do a molecular dynamic simulation. So you can see that, okay, initially this is running a very high temperature of polyethylene. So you can see that initially you have a plastics, and the plastics will break down. They generate a small olefins, and then the olefins break down, they generate ethylene, and eventually could generate aromatics. This aromatic is formed, and then you don't want this. So if you're looking at the time scale, at a very short time set, 0.5 nanosecond, but the temperature is very high. And you can see a very high yield of C1 to C4 chemicals. And if you go to a longer time, then a lot of carbon is formed, and you don't form much the chemicals you want. So therefore, we want that the heat that the plastics, and then stop here, so that synthesize that the C1 and the C4 chemicals I want. So here that is the idea. So you have the plastics, and then you melt it by heating, electrical heating. And you have this carbon fibers. That carbon fibers play a role, is like a siphon. They suck in this melted plasma and then siphon it to the top. And on the top, you have a carbon fiber heater. This is a carbon fiber. You pulse it, and to the peak temperature about 800 C, and then you stop it. So this is the polypropylene, and then you want to break down into propylene. And we achieved 46% of yield, and twice of any of the existing commercial process. And this one is a polyester, and we can cut the polyester. We generate a 43% of yield. So to doing that, you can see that this is polypropylene and generation. This is that all different kind of other methods in the literature or industry. And either generate below 10%, or some with catalysts generate barely 20%. And we can go to 46% by using non-equilibrium manufacturing. So this is the one I try to show you example that by manipulate that the chemical non-equilibrium, you can do something and you cannot do it before. This is that advantage about electrified manufacturing. But of course, you have disadvantage compared to combustion. Because combustion generates a lot of power, and so that is a disadvantage. But you can use it in a niche area, and you can do something. And the same thing that we say that what if that we do something using a non-equilibrium heating to generate chemicals. And here that is ammonia synthesis. You can put a nitrogen and a hydrogen, and you put a catalyst on the surface, and you pulse it as a function like that. You try to understand how much that the ammonia is produced. So you can see that between using different catalysts, you can form probably 6,000, 4,000. But if we compare, this is that the method we have by using pulse, heating, and quenching. This is the yield compared to the yield of other. So by just using a very simple catalyst, so you can, using this non-equilibrium heating and quenching, then you can reach to the best yield of ammonia in atmospheric pressure. So this gives you another indication that by manipulate non-equilibrium process, and you can enhance the yield of ammonia and increase the selectivity of plastics and methane pyrolysis. So how can we do better? Well, to better, that means heating is just heating. And can we drive far equilibrium, non-equilibrium? So that is the opportunity about the plasma that it can drive far from equilibrium, that generate not only heating and quenching, but also excite that the molecules and electrons, so that it can do something, and the heating and quenching cannot do it. So this is the diagram. I try to show you that what is that reaction, catalytic reactions. Everybody knows that in reaction, you have reactant and you have product. And you have a transition state and you have activation energy. So in combustion, this is that the activation energy you have to overcome in gas phase. But if you have a catalyst, for example, because that the particle molecules can absorb and react on the catalyst, in that way that your absorption energy, that could be positive, could be negative. So, and this absorption energy and then the catalytic reaction pathways allow you to do something that it cannot do it at the same temperature. So this catalytic reaction and surface absorption and provide you a new reaction pathway that, for example, nitrogen, that can absorb and dissociate on the surface instead of pyrolysis in the gas phase. So this energy barrier could be dramatically smaller than the energy barrier of gas phase reaction. So if we can using plasma to drive the excitation of this reactant, we can further reduce the energy barrier of catalysis. And there was a paper published in Nature, Catalysis, and 5-6 years ago. And what this is that time that I think that the ammonia was very, very hot. And they basically say, okay, this is that the surface absorption, dissociation energy. And here that is very weak. There's no absorption. Here is very strong. If the species is very strong, then what happens? That the nitrogen atoms is a stick on the surface. They never go away. And then the catalyst side will be occupied and no reactivity. And if the absorption is too low, That means that the molecules collide on the surface and immediately go away. And you don't have anything on the surface, your reactivity is also going down. So therefore, there's a peak surface adsorption energy, and so that the reactivity is strong. For example, ruthenium, they provide the good adsorption and dissociated energy, so that you have a high, the TOF is not time of flight. It's a turnover frequency. That means that it is reactivity. So, but what's the theory says that if you increase that the process by using plasma, and what it says that by doing plasma, and you can increase that the reactivity by orders of magnitude. So that's what the figures says. So plasma enable catalysis by, this is log function, by several orders of magnitude. So this paper and presented a result based on estimation or analysis and create enormous hope that plasma is a game changer for ammonia synthesis. That's why that the Nature editor probably liked this paper and published it in Nature Catalysis. What I try to say is that Nature and Science are good journals, but that not necessarily the papers are great. And sometimes, most of the case, they just, I didn't know that, I have been publishing when I was like your age and before probably 4 to 5 years ago. The only journal I considered was Proceedings of Combustion Institute, Combustion and Flame, that AIA journal. That are probably 3 journals mostly I published. If you check my publication record, I published lots of papers in these 3 journals. But later I found that, if you want to persuade others in different fields, and you better to publish somewhere else. So that we try to, collaborate with people to publish on Nature. And since probably 2019, we published 5 to 6 on Nature. Now I start to understand and how that the Nature Science, you have to have a great news so that editors like it. Otherwise, they don't publish a paper, no matter how good the science is, right? So I think that is that the guy published a good news saying that plasma catalysis is going to change, the game changer to change that the ammonia synthesis by several orders of magnitude. This is wonderful if it can happen. And then now we try to say that what is that the fundamentals of catalysis. So many of us are doing combustion, but some of you maybe in the future, you jump into the area of catalysis. The catalysis that you always involve a surface. For example, if you have a molecular, and that molecular and collide with the surface, and they absorb on the surface. And this is that a Langmuir absorption. So if we write down a gut reaction, if the combustion people, we love reactions, we say, okay, we have a molecular with a surface site, and then absorb to the surface. And you assume that the surface site absorbed does not change. This is called the surface absorption equal to the concentration of A times that the reaction rate, times that how many open surface available, and minus that the desorption process. So if you assume that this absorbed surfaces is quasi-steady state, in other words, that the rate of absorbed on the surface compared to the rate desorbed is much slower. So therefore, this concentration does not really change. So by taking this one equal to 0, you can solve that the surface absorption site, theta A. So you can find that the theta A is a function about the reaction rate and equilibrium constant. And then this will give you an estimate how much the surface is occupied by A and how much open surface is available. And so you can see this is strongly pressure dependent. And it's a high pressure, and the CA is high, and then the surface side is very low. So therefore, the pressure affects that surface absorption and then side density on the surface. The next thing you want to say, okay, what if I have a nitrogen that is diatomic moleculars? So I want a nitrogen to adsorb on the surface, and then they become 2 nitrogen atoms that adds a surface. And then I have a hydrogen come in, I can dissociate and form ammonia molecules. So this is that way you can write down equation, a nitrogen molecule with two surface site and become two atomic species adsorbed on the surface. And you assume that the nitrogen atom on the surface, again, is a quasi-steady state. You can write down this a reaction rate and take it to 0. You can solve it into the surface site of nitrogen atom is proportional to the square root of that the concentration, because that is the diatomic molecules. And then you can write down what is the open site is available as a function of pressure. So diatomic molecules are more weakly dependent on the pressure. So you understand the process. And the next thing that is important, that is the multi-species, right? It's not just a nitrogen, but also have a hydrogen. So let's say that I have molecule A adsorbed on the surface, molecule B adsorbed on the surface, and then on the surface they may react together to form a new species called AB. So in that way, you can write down that each species using reactions, and you assume they are quasi-steady state, which is normally true. And then you can write down all the surface open site, and A and B, there should be 1. And you can find a solution about that the open site on the surface is proportional to the inverse of the reaction rate and A and B to the surface. And then you can write down how much surface site occupied A, how much surface site by B. And they compete with each other. And so there will be not only a strong pressure dependent, but also you have a good molar ratio between A and B in order for the reaction of A and B to happen to give a high catalytic reactor. So this catalytic reactions is a strong function of that. So then we talk about a longer, more Hessian word. It's called LH mechanism. So you say that it says I have molecule A and adsorbed on the surface, molecule B adsorbed on the surface. And these two surface species, they react. And then they dissolve into a molecule. This is the LH mechanism. So this is one of the three dominant catalytic reactions and being studied. And so you can write in the reaction A adsorbed to the surface, and B adsorbed to the surface. And A and B, they react with reaction rate to the A and B. And then desorption assumed to be very fast. If it's not fast, then your catalytic reaction is very slow. So you can do the same, and the combustion people are so smart. You can do a quasi-steady state for all these species and find that the open site density, and then you can calculate the catalytic reaction rate equal to the K times the A star, B star on the surface, and this is the reaction rate you can have. And now it's proportional to the square of the concentration. So this means that this reaction is much more dependent on the pressure. So this is how that pressure A and pressure B, partial pressure, affect the reaction rate. So you have to have an optimum concentration of A and B, and also is much stronger pressure dependence. So when you have a LH mechanism. So another mechanism is that they call Ehlers-Danlos mechanism. So that is I have a molecule adsorbed on the site, and I have a radical, let's say H radical, in the gas phase. And then this is at a surface, and they react with not on the surface, but in the gas phase, they form a surface and then dissolve. I love this Ehlers-Danlos mechanism because you involve a species or gas phase in the gas phase. That my combustion chemistry, my gas phase chemistry strength is going to be reflected here. So that we become we try to study LH mechanism, my God. So then the chemical engineers are much stronger than you. But if you find that the mechanism process is Ehlers-Danlos mechanism, you should find that you have a great advantage because you understand that B much better than other side. They probably understand the A better than you. But then we learn this. You are on the interface. You have your advantage. So it's always like a research, like a competition is a battlefield. You have to know what weapon do you have, what their strengths they have, and how do you win in competing by bringing unique tools and to the battlefield, right? So this is something you always have to think about it. So you can write down a simple equation. A adsorbs to the surface, and B is in the gas phase, react the species on the surface, form AB, and thus. And they do this. And the chemical engineers, they can do equally well as we do in terms of writing down the equations, analyze what the reaction means. But I think that we have much better gas phase kinetics. So this, again, is a pressure dependent, but not as pressure dependent as the LH mechanism. So if at low pressure is proportional to the pressure of the product of both reactant, at high pressure, they're only critical to B. So this is very good. That at high pressure, and which most of the systems want to be, and it is very critical and to that species concentration in B. So what I can do, I can control B by using pulsed heating. I can control B by using plasma. I can control B by photosynthesis for photoionization. So that creates a lot of magics I can do, and it can affect this thing. Another mechanism, before I take a break, is that the MVK mechanism. The MVK mechanism is wonderful that they say, I have a surface gas phase species, and this is my surface. And then if there's a vacancy on the surface, my molecule come in to the surface. For example, if I have nitrogen, and this is a nickel, nitrogen will come into the surface. And then I have a hydrogen. That hydrogen gas phase, it come in to react with that the nitrogen absorb on the surface and form a product of NH. I just love this reaction so much, because not only that the gas phase is important, but also they involve that the interaction between gas phase and the surface and change the materials itself, right? This is that interface about that the heterogeneous reactions. So I just submitted a proposal to NSF, and I said I have wonderful idea to control the surface vacancy and create a new mechanism by using plasmas. I called a name, of course. I always give a name. And we'll see how it goes. And so what do I try to say that combustion people, you are trained, you're so smart, you can understand a lot of gas phase chemistry and reactive flow simulation tools. But do pay attention to materials. And what I try to say, when I was a college, the people write down in announcement, say mechanics is dead, right? That was why I was graduate student, was like 30 years ago. Is the mechanics dead? Obviously not. Is the mechanics not dead? It's not also true either. So the classical mechanics indeed is dead, right? You look at heat transfer. When I was graduate student, everybody measure radiation, measure convection coefficient, just like we measure flame speed, measure Grashof numbers, measure all these things. All this entire field is dead. And heat transfer goes to bio, goes to nano, right? Working with materials. See what I'm saying? Then you look at that solid mechanics. When I came to Princeton, the people tell me solid mechanics is dead. Just do micro solid mechanics. They do microstructures, non-continuum materials, fractures. But after a few years, that area is dead. And they'll go to where? They go to soft materials. And I found that a very famous professor in mechanics reading a combustion book. I said, why do you read a combustion book? He said, you know what? The solid mechanics, stretchable materials is so hot, polymers. And then when they stretch it, they involve reaction, the bond breaking. That's a reaction. I need to understand reaction. So you see that the research area is always changing dynamics. You have to be a pioneer in that field. Lead, that is the change. Advocate the change of the society. But no field will die. But they only evolve in a different phase, right? And the fluid mechanics is the same thing. When I was a graduate student in Japan, every department hired CFD people. And they can calculate aircraft, they calculate shock waves, wind tunnels. But none of them right now is active because that area is gone. You cannot say that I just love it. I want to do it. No. And these people, fluid mechanics people, you look at our department, the fluid people, what they do? They do a microfluidic, bios, have cells in the moving. They do aerosols in the atmosphere, in the climate. They do the ocean waves. How do they generate droplets from there? They see that how CO2 is dissolved in the ocean. It's completely different fluid mechanics. It's not dying. You have to welcome the change. That is the message I want to say. Okay, when you are young, always welcome the change of a new field. All right, let's take a break and come back.